please.
Well, first I want to thank Katya and Knut for inviting me, but more importantly, you know, this seminar has been super important during the pandemic. I mean, I remember at the beginning when we didn't know at all what was going on, and whether we were going to see anybody, you know, we were in our own little pods, to be able to come to the seminar and see friends like I see here now. So I really see this seminar as a real service during the pandemic. And I'm also happy to hear that it'll continue, you know, now that the pandemic is hopefully waning. Good. Okay. So this is work from sort of over several years with friends of mine in Karlsruhe, Christine Gothwald, a graduate student, Herr Kunstmann, and Andreas Rieder at KIT. And it's supported for their work by the Deutsche Forschungsgemeinschaft, my work, the NSF and the Simons Foundation. And so I'm happy to announce them. Now, we're going to study an inverse problem for the wave equation. And you can see it on this lower right here. I'll do it again because it's sort of cool. A wave coming out. This is with constant wave speed, and you see how it reflects back. And anyway, if you have t a point x in RD, where d will be 2 or 3, mostly 2, at time t greater than or equal to 0, from a source xs, which for us will be on the surface of the you know, of the Earth or the water. And if Vp is the speed of sound with objects in the ocean, then we have the acoustic wave equation written here, where xs is the excitation, and it's the excitation point or the source point, and then we're measuring backscattered, that is reflected fields, where we have a point, of course, xs here and xr over here. Okay, I think I know what's happening. And we observe it for just a fixed amount of time, nearly from 0 to t max. Okay, we make a simplifying ansatz that is very common. Remember, Vp is the actual sound speed, the so-called perturbed sound speed, when you have stuff in the ocean. We choose a velocity v that's smooth and known. And in order for this ansatz to work and give reliable reconstructions, our velocity shouldn't be really super different from the background, at least if we're going to use the wave equation model. Good. And n is sort of the high frequency content. So this thing here. And so we assume that they're close, and the perturbation is just this function n. And our goal is to determine that, because that'll give us information about the objects. Okay. Now, the travel time, if we have a source xs and s, is the time it takes to travel along a geodesic from the source to the point. And that's important. Now, the velocity that can determine the travel time by this equation, that the magnitude of the gradient in x of the travel time is the reciprocal of the velocity, with the initial condition that the travel time from a point to itself is 0. And in general, you know v, and you need to find tau. And one limitation about our method is that we need to actually have analytic expression for tau. at least for what we've done so far. Okay. So a standard thing that, for example, is in Syme's really valuable unpublished notes, that this operator, we call it f of n, is an integral of u tilde minus u evaluated at what the source s is, where s is a variable that determines both the source and the receiver, xr and xs, and then xr, xs, or s, sorry, s is time, I'm wrong, I was thinking later on, where u tilde is the solution to the wave equation for the known velocity v that we chose, that's that we have an expression for and is close to the perturbed velocity v sub p. Then Syme shows that this operator can be written as our function n that we're looking for over the known velocity times this function a, where a is given by the div of a squared del x of tau is 0. And then for each t, we integrate over the surface, over the surface of points where the distance from xs to x and then to xr, that sum is equal to t. Good. Okay. And this expression shows that f can be viewed as a Radon transform. Namely, this delta says that we integrate over this isochrones, namely the curves t equals tau of xs dot plus tau of the point x xr. So we integrate in the plane over curves and over surfaces in R3. And so that's good. But also, if you take a Fourier transform in t and omega, the dual variable, you get this expression, which under certain conditions is a phase function of a Fourier integral operator, and that turns f into a Fourier integral operator. Good. Okay. For convenience, we're going to specialize to R2, although some of our work is valid in R3, and we've already done it. Maybe talk a little bit about that later. And so we assume the velocity is known, the background velocity. We assume n is square integrable, and the perturbation, the high frequency components of the perturbation, are compactly supported. And incidentally, conventionally, the x2 being positive goes down from surface. Okay, now we consider a standard geometry called common offset. And what this geometry is we choose an offset, a positive number, and we take the source s minus alpha 0, and the receiver at s plus alpha 0, and parameterize it by s. And so we move s and we move the sources and receiver. Now, they don't always take data this way. The geophysicists tell us that from the data they do take, it's the ones in Karlsruhe, you can get this common offset data. Good. Now, in most of the talk, we're either going to consider constant sound speed, or we're going to consider affine sound speed in depth, so that our velocity only depends on the depth and depends on it in an affine way, where since a is positive, the speed increases as we go down, but it starts greater than 0 because of the beat. And the reason is in both cases, there are analytic formulas for the travel time which allow us to do our calculations, which depend on the travel time. Now, this v of x, the affine, might seem like a big restriction, but actually some geophysicists in layered media, namely where the velocity is constant along horizontal lines, only depends on the depth, they'll approximate that by affine wave speed and then use that to reconstruct. Good. So that's one reason to study the affine wave speed. Okay. For the first part of the talk, we'll talk about constant wave speed, and like all mathematicians, we'll simplify, say the velocity is 1. And so the travel time between any 2 points is just the distance between them. And then the isochrones are ellipses, because if we take a value of t and the sum from xs to s plus the distance from x to xr, that sum being constant, that describes the isoclines. And as you remember from junior high, maybe, this describes ellipses. So in other words, you integrate over ellipses with foci xs and xr. And then if we move from like S1, 0, S1 being the parameter, to S2 being the parameter, we get a different set of ellipses. Just shifts of the ellipses on the left. Okay. Now, so we're going to talk a little bit about the elliptic transform. I hope that's approval, whatever that dog said. Okay, and again, we're 2D, offset alpha greater than or equal to 0. The generalized Radon transform becomes the symbol n of x, this delta, where phi is the sum of the travel times from xs to x plus xr to x. And phi is the symbol, which in this case, that expression that gave us the symbol is especially simple. The velocity is 1, and the a function we saw earlier is easy. So note that this symbol, well, when we write it in Fourier form, doesn't depend on, only depends on x and s. Good. Okay. So we're going to let the data that we use be some S0, or later we'll use S prime in R. There's going to be a bound and open set of parameters for the source and receiver pairs. So our sources and receivers, the common offset, don't go all over everywhere. They go in a compact set, which we can only measure that way. And so the reconstruction operator, this is the operator we developed in an article of ours in 2018. We consider the following operator. F is our forward operator. F dagger is a generalized back projection. You know, back projection of a Radon transform, you just pick a point x and take integrals over all of the manifolds you're integrating over that go through x. And so that's what the u of s, we integrate over parameters s. Phi of sx, that describes the isochrone that goes through x and parameterized by s. So we integrate over all isochrones through s. And w is a weight. It could be the weight required for the adjoint, the L2 adjoint, or it could be another smooth function. We want to make it arbitrary, so for a reason we'll make clear soon. Okay, so W is a smooth positive weight. Now, psi is a smooth cutoff, so we can compose F dagger and F, because in general they can't be composed because F goes from compactly supported distributions to distributions, and F star goes from compactly supported distributions. So we have to take a compactly supported cutoff so we can compose. Also, that's realistic because we only have bounded sets of measurements. Good. Okay, and K is going to be a properly supported pseudo-differential operator. And we're going to give it a positive order in general. And I'll remind you later on that we'll call it symbol little k. Okay, whoops, sorry. Okay. Now, F is our forward operator, F dagger our weighted back projection with weight W, K is the pseudo-differential operator, and psi is the cutoff. It turns out this is a pseudo-differential operator of order m-1, where m is the order of K, and I remind you we're in R2. So F dagger psi F has order -1. Okay, this is pretty well known, and I'm just recording it here. But under the Bolker assumption, which we'll talk about in a minute, it's that pi L, the projection from C, the canonical relation, to T star Y is an injective immersion. Any hypersurface radon transform in d-dimensional space composed with a formal adjoint or a smoothly weighted adjoint or FIOs of order -1/2. And actually d dimension should be, in this case, R2. And R2, RD, it would be d-1/2 or negative d-1/2. And this was well known from Gilliam and Sternberg's really seminal work in 1977. Okay. And in general, if you have two Radon transforms, R dagger and R, satisfying Bolker, and they can be composed, for example, by putting a cutoff in the middle, then you get a pseudo-differential operator. That was the result of the Bolker assumption, which Gilliam and Sternberg proved, and others of us, myself included, have used it as well. Many people have used it, actually. Okay. Now then, R transform F satisfies Bolker, and in R2, an article of Christian, myself, and others show that. In R3, an article of Fillet and myself and others show that. And actually, there are other articles that we should have added that show this, basically show this as well. I apologize for leaving them out. Therefore, in R2, F dagger psi F is a psi DO of order -1 from these general results. And K is properly supported, has order M, so the whole thing has order M-1. Okay, so this is good, it's known. Now, one of the things we do is we calculate the top order symbol. And it's 2 pi, which is an appropriate normalization. K is the symbol of K, big K. Well, I hope the dog likes the talk. And psi is a function of S and the value of T that corresponds to S and X. W is the weight, and big theta is the symbol, and we divide by omega, then B of Sx, where B of Xs is the Belkin determinant. This is it. Now, the rub is we need to know what S is and what omega is. Implicitly, it's defined by C, the vector that we chose is omega times the gradient in X of phi of Sx. Okay. Now, here's a picture that'll show what it looks like. We have a point X. We have the psi. Now, it's normal to an ellipse, one of the ellipses in our data set. That determines S. And by geometry, there's a relatively simple relationship. And C is a multiple of the gradient, because the gradient's also normal to the ellipse. And omega is given by this. And so now that we've determined S, or have a formula we can give to determine S, we get the symbol at XC. The good thing about this is on the next slide. But first, I should mention, this follows a general calculation of an old article of mine where we expressed the symbol of generalized Radon transforms in terms of their defining measures. This followed from Gilliman's seminal work, and it was focused on the calculation of the symbol. And it's now completely standard microlocal stuff. Good. Now, we did this calculation in R2 and R3 in a 1980 article with Grathwohl, Kunstmann, myself, and Reader. I think it appeared in Inverse Problems, either that or Sims. I forget which for this article. Now, the useful thing about this was by knowing the symbol of that pseudodifferential operator, we discovered that unless we adjust the weight, the symbol depended, the magnitude of the symbol depended on the depth. So we adjusted the weight so the magnitude depended less on the depth. That was the advantage of calculating this. And we used this to adjust the weight and got better reconstructions. I'll show you something here. Now, there are a lot of things here. Microlocal properties of F and these and a bunch of geometric steadings. These are by no means everybody, but Belkin in the beginning in his important 1985 article, Rakesh, Nolan Symes, Tim Kruda, Stolk, De Hoop, and then Krishnan and myself and others and Falea. We've also done work on this in R2 and R3. Good. Okay. Now we get to affine velocity. That's the new word in an article that'll appear this year. And again, affine velocity is the velocity equals is affine. Well, you get the picture. Now, the deal is the travel time is explicitly given. And this is in an old book, a calculation. And so we can use the travel time to define the phase function, and we can do explicit calculation. Okay. Now, we have domains where x min is given like this. And I should note that if alpha equals 0, x min is 0, and t min is 0. If alpha is equal to 0, the source and detector are together. And x min is the point we want the support of our function to be below it. So if alpha is 0, there's no restriction. But if alpha is positive, there is a restriction. We'll see more on the next slide. Okay. Now, the value of S and T parameterize the isochrone. I of ST is just the points such that T is the distance from XS to X plus the distance from X to XR. And this isochrone for the value T min is the trivial isochrone with just the geodesic. That's why we exclude that, and we certainly don't have anything shorter, any isochrone shorter than that. Now, on the next slide, we'll explain why if x2 is less than x min, namely, if the support of our object is above this x min, there can be problems. F is not well behaved. So here's a picture with wave speed given here. And we take several isochrones. We take one with t is 8.4, and you can see the top part of the isochrone comes into the reconstruction region. The reason is the velocity is faster down here than it is if it were to go up. And so the top half goes down because that's a faster way to get here. So if t is small, the top half can go down. You see that in the green isochrone, the t equals 10 blue isochrone. And then at 12.5, the isochrone actually just goes above, the top half. But if both halves of the isochrone intersect the support of F, then you can get a problem. Oh yeah, sorry, I'll come back to this. So this is x min. But if you have an object that looks like this, wavefront up here can cancel or add to wavefront down here. So in other words, you can get artifacts caused maybe up here by wavefront down here and vice versa. This is so-called mirror points you see with the elliptical transform and circular transform with sources on a curve or surface. Okay. Now, so that's why we take t x less than x min. So our object is down here, not above. Okay, good. Now, we're going to define phi alpha is just the travel time from the source. This is the source to x plus the travel time from x to the detector. Again, we're talking about general travel time. Then this parameterizes the isochrone as we saw before. And we saw pictures on the last slide. And if you remember our what we presented at the beginning, our F alpha, where alpha is the offset, is this expression. Theta is the symbol we wrote down or described at the beginning. N is the function we want to recover. And we have this as phase function. The symbol has order 0. We saw it on a previous slide that actually this theta doesn't depend on the phase variable omega. So it's order 0. And the phase function is often a non-degenerate phase function. The projection on t star y is fine because of the t is isolated, but we need to know that phi alpha defines the gradient in x that phi alpha is non-zero, which is an appropriate condition for the isochrones to be well-defined smooth curves. Okay, good. And here's the canonical relation. I mentioned this because we'll need it in describing the proofs. So we have S and T, the y parameters, the S derivative, the T derivative, X, and the negative X derivative. And the condition is T is equal to phi alpha of Sx, namely X is on the isochrone parameterized by S and T. And of course, omega is non-zero. So that's good. We need to learn what the properties of the canonical relation. Now then, an important condition we've mentioned before, and I'll define now. F satisfies the Volcker condition if the natural projection pi L going from C to T star Y, namely T star of the data parameters, is an embedding, an injective inversion. Okay, now our reconstruction operator, K's pseudo-differential operator properly supported, F dagger alpha is weighted back projection. Psi is a cutoff. So F alpha and F alpha dagger can be composed. Now, the reason to consider this sort of operator, we actually said it before for zero or for constant velocity, is that when F alpha satisfies the Volcker condition, then this is a pseudo-differential operator. So it has many properties of differential operators. For example, the wavefront set, oh, I thought I got this, of K, sorry, K F dagger alpha F is contained in the wavefront set of F. And what that means is the reconstruction operator will image at least some of the singularities of the function F. Oh, where F is actually N before, but doesn't add artifacts. You know, in many problems when Volcker doesn't hold, you can get artifacts, like in the elliptical transform if the data is both above and below the source curve, or the source line. Okay. Now, here's one of our main theorems in our recent article. For affine wave speed, F0, the zero offset operator, satisfies Volcker. So that's good. That means that all the stuff I told you before about this reconstruction operator, it's going to be an FIO, and so we don't get added singularities, and we do recover at least some singularities about depending on size. Okay. Now the proof consists of subtle calculations, and because the travel time is more complicated than constant velocity, you know, constant velocity, the expressions are a little complicated, but they're less so than here. And all the complete details are in our article. Well, here's a conjecture. Maybe for some or all positive offsets in affine wave speed, we conjecture that F alpha satisfies the Volcker assumption. Now, I want to talk about this and explain it using, and it's in the process, we'll sort of outline important parts of the proof for alpha equals 0. Okay. The proof for F0, alpha equals 0, starts by parameterizing the isochrone. I'm going to use the plus, which isn't clear here. We don't really need it, but x plus of theta is a point on the isochrone, I of st. And so we can parameterize it by a sort of angle going around. Then we show that the the derivative in S of phi 0 at x plus is strictly increasing. Now, I claim, at least if t is greater than t min, I claim this determines the only unknown coordinate in the canonical relation. So as we look at the canonical relation, it projects to pi L st negative omega gradient s of t0 omega. So From this, we know, from the projection, we know ST and omega. The only thing we're missing is X. And however, we do have this coordinate. And we do know that X is on the, is on the isochrone, parameterized like this. So by knowing this, we show in offset 0 that this function's a strictly increasing function of theta, and therefore there's an inverse function, and it's smooth. By the inverse function theorem in one variable, so we can figure out theta, and that gives our point on the isochrone, and that gives us the only coordinate in C we didn't know. Good. So that's the proof for 0. And the calculations for alpha positive are more complicated because certain cancellations don't exist. But numerical experiments that Andreas did showed that this derivative seems to strictly increase over a range of alpha, A, B, and T. Now that doesn't prove anything, but it suggests, and so that's why we made the conjecture. Luckily enough, we have some more to say about the conjecture. Okay. Now, a theorem I wasn't aware of, but of course, once we proved it, it makes perfect sense, that if the phase functions are close, the operators are going to have similar properties, namely, in particular, in relation to Volcker. Let X be an open subset of R2 plus and S prime an open subset of R. Phi j are going to be smooth functions. They're the ones in our problem that define the isochrones. And we assume the phase functions for each j are non-degenerate, and the operators we get are FIOs. Oh, and we have j be an FIO with this phase function. Now, we take precompact subset of X, precompact subset S of S prime, and if phi 1 is sufficiently close to phi 0 in C3 norm, then the operator F1 satisfies Volcker. Okay, here's something that if I was in a class, I'd ask, what did Quinto forget here? We need to assume that F0 satisfies Volcker. It's not magic, it's math. So I'll assume F0 satisfies Volcker. Then if F1 is sufficiently close, F1 will satisfy Volcker. Before we go through the proof, let's state a corollary. So assume we have a travel time and assume the 0 offset operator satisfies Volcker, for a given open to S and X and S prime. Then we take these precompact subsets. Then there's an alpha 0 such that for all alpha that are sufficiently small, namely between 0 and alpha 0, F alpha satisfies Volcker, at least on gamma or above gamma cross S. I'm being a little sloppy here, but it means functions supported on gamma and our center set S. Good. And so the point is, this answers our conjecture, at least for small positive wave speeds, because f0 for affine wave speed we showed satisfies Volcker. And therefore, for small offset, small positive offset, it does too by this corollary. And the proof of the corollary is if the offset's close to 0, then the function phi alpha, the sum of the travel times, with these offset source and receiver are close to the ones if they were together. Now, the proof of the theorem at the top of the page, namely, if the phi j are close enough, and one satisfies Volcker than the other does, goes like this. These phase functions are structured enough that we can use the same set of coordinates on both for both operators and both both canonical relations. So this here is the canonical relation Cj of Fj. And the idea is, if the phis are close, then when we use our coordinates, comparing coordinates, the phi1 of certain coordinates is going to be close to the phi0 of those coordinates. And if the phi0 are close enough in C3 norm, then the projection operator is going to be close in these global coordinates. And then, since pi determinant d pi 0L is not 0 because the pi 0L is an immersion, and this determinant for pi 1 is close, it'll also be bounded away from 0, at least on these pre-compact sets omega and s. Okay, so that means that pi 1L is an inversion, and therefore pi 1L is injective above any ball of sufficiently small radius with centers in omega, in x. And this is sort of a leg number. When we have a pre-compact set, we can cover its closure by these open balls or open sets on which the pi 1L is injective, and we can find an epsilon such that every epsilon ball with center in omega will be in one of these sets. Therefore, pi 1 is injective on every one of these epsilon balls. Okay. Then we show pi 1L is injective by using that pi 0L is globally injective, and they're close. So if the pi 1s agree, of 2 points, the pi 0s are going to be close. Therefore, the 2 points, Sx and omega, have to be close. And making phi 1 and phi 2 close enough, these 2 original points will be in one of the balls. And actually, that should be x cross s. Okay. Good. As our final thing, actually, in case that was too fast, the basic idea is if our phi j are close, our functions are close. There are projections pi 1L and pi 2L. And if one is injective, at least on pre-compact sets, and they're both immersions, then the other one will be forced to be injected, because points that would map to the same point under pi 2L have to be close together. And that was the point. Now then, this gets back to what we were talking about at the beginning, how to get a reconstruction operator. So for affine velocity, we develop a reconstruction operator. We're going to use is our K delta. And then we're going to create weighted back projection. And here's F0 dagger. And then here's psi and F0. So psi is the cutoff we talked about. F0 dagger is a back projection with weight adjusted to provide more uniform symbol of this gamma in depth. So in other words, we actually did calculate roughly the symbol of this gamma operator and adjusted the weight of the back projection so that the symbol was more uniform. And this is a reconstruction. And just to convince you I'm not using the inverse, doing the inverse crime, the data wasn't generated using radon data. In other words, taking the radon data interval over isochrones. It was generated using the wave equation and the unperturbed sound speed, the background speed, was this. So when we look at the object, it was a square above an ocean floor that's, you know, like a cosine or something. And what this showed is that our reconstruction operator, at least in this case, did a pretty good job reconstructing. So this abstract stuff was helpful in making a good reconstruction operator. Good. Okay, so in summary, in the 1918 article, yeah, 2018 article, yeah, not that old. For constant wave speed, we calculate the symbol of the reconstruction operator, and we develop a more uniform reconstruction, uniform in depth. And in that article, we give plenty of examples, but I was more interested to talk about our new article, where we consider affine wave speed, which is useful and more general than constant. And zero offset, we showed the seismic operator satisfies Volcker. Then we showed that the travel times are sufficiently close in C3 norm, and one operator satisfies Volcker than the other does. Or if the, oops, sorry. Also, we related the fees actually. And we did phi alpha and phi 0 are close. In general, phi 1 and phi 0 were close if the travel times were different. And if the original travel times, phi 0, are satisfy Volcker, and the phi 1 or phi alpha are close for offset. Then the other one does. The one, the operator corresponding to the phi 1 or phi alpha. And we use this to show in general that, right, the zero offset operator satisfies Volcker, then for small offset it does. So Volcker holds with small offsets in affine velocity. Our conjecture is at least true some of the time and maybe more than that. Since we don't have an estimate on alpha 0 on how far it is, you know, that would be something interesting to try to do. Okay. Also, we do a result that's fairly technical about the velocities. Namely, if the velocities are close, remember they generate the travel. If the velocities are close in C5 norm and the travel times in geodesics satisfy some conditions to mean that they're well behaved, then if the velocities are close enough, the travel times are close enough. So if one of the operators we talked about, like F0, satisfies Volcker, then F1 can, at least if the velocities are sufficiently close. And in other words, closeness of the velocities implies closeness in C2 in C5 norm implies closeness of travel time in C3 norm under these rather restrictive, but okay assumptions. And I'm happy to say this is going to appear here in Applied Mathematics Quarterly, honoring my advisor, Victor Gilliman. Editors were Gunther Ullman and other people. And finally, I say thank you for your attention. Okay. So I guess we ask for questions or comments or.
Yeah, great. Thanks so much for an excellent talk, Todd. So Katja is inside of the passport office, so I'll run the question session.
Well, I hope she makes it out okay.
Yeah, let's hope that she solves that problem. So, but thank again for a great talk. So, if there are anyone that have questions, please unmute yourself and ask questions. So I was wondering, is it somehow possible to say something about the resolution you can achieve in the reconstruction? Say the psi, for instance, the cutoff, will it affect the resolution in some sense?
Good question. Yeah, you can. Let me go back. Well, okay. By resolution, I mean, there are two ways of interpreting. One way is if how close the function is to the reconstruction, but we're interested in reconstructing wavefront sets, and we're interested in reconstructing at least shapes. So I'm going to do the other one, which is maybe more appropriate for our philosophy, and that is, I can just point to a slide. Sorry, you can close your eyes until I get to it. Okay, here it is. The psi, you're exactly right, determines what singularities you're going to see. And so the psi appears in the symbol. So if you know psi, you can then say these singularities will appear because the psi is non-zero. But these singularities won't appear because the psi is zero. So that's an easy thing you can say. Also, I didn't say it, but because of Sobolev continuity and microlocal ellipticity, you could also say something about the Sobolev strength of the resulting signal. The resulting.
Thanks.
Sure.
So please unmute yourself if you have your questions. Oh, well, if there are no more questions, let's thank Todd once again for an interesting talk. I hope Katja makes it out, but let me thank you by also on her behalf. We will have one more talk next week, and then will be a break again. So thank you again all for coming to the seminar today.